Hi, this is Mr. Merrill. In this problem, we're going to calculate average power. So, power, to remind you, is the rate that energy is transferred in or out of a system. And based on that fact, the equation for average power should be pretty intuitive. In the numerator, you have the energy transferred. This is basically the equation for work. And here on the bottom, we have time. So the problem only becomes difficult when we get to the issue of solving for time, because energy conservation alone does not involve time. You just have this initial picture and this final picture, but the time doesn't come up in any of the energy equations. So when we're asked to solve for average power, we're not given for time, we usually have to involve some type of kinematics, and it's usually kind of a pain, but it's all stuff that you've done before, so just work through it carefully. So if you haven't watched the last video, we calculated what that top number should be. That's essentially this portion, this mu k mg cosine 37 degrees. That is the magnitude of the frictional force, mu k, times what's substituted into being equal to Fn, times the distance. That will be this 5 meters here, the distance the force is applied over, and we need to simply find the time that the force is applied over to calculate the average power. So the time from when the hammer is at the top to when the hammer is at the bottom of this roof. So how are we going to get the time? It's not given the problem. Well, we can think to our kinematics equations and wonder which of them will be useful to us. So here we have something where we know the displacement, and if we knew the acceleration, we'd be able to calculate the time. There's really no kinematics that is just going to instantly give you the answer. But we can calculate the acceleration. All we need is a force diagram. So we've seen this before. Here's a force diagram for the hammer as it goes down the ramp. You can see the components are written out here. I generate two equations, one for the y direction, one for the x. Substituted the components. This is just sum all the components in the y, sum all the x. I do a little bit of substitution. The masses end up canceling, and I can numerically find the acceleration. Go ahead and calculate it yourself to make sure you get the same thing. So I got an acceleration of 2.767 meters per second squared. So hang on to that number. And then I can go back to this kinematics equation, rearrange it to solve for time, plug in that 2.67 meters per second squared for the acceleration and the 5 meters for the displacement, this portion when it goes down the roof. And now I have all the numbers that I need, plugging in the values that are given in the problem. I get an average power, an average rate of energy transfer from kinetic friction of negative 16.47 watts. And remember, a watt is a joule per second. So what this is saying is, for every second that friction is applied to that hammer at that angle, it is removing 16.47 joules of energy on average. You also have a problem where you have to find instantaneous power. The only difference is, instead of finding the time, you're often charged with finding a speed, and oftentimes, again, it's a problem of finding a kinematic equation that works, and usually using a force diagram or something along those lines to get an acceleration to finish off your kinematics. So it's a long problem, but it just has pieces of things that you've done before, and it's just a matter of bringing them all together. Alright, so hopefully that was helpful.